Chapter 16, Section 1 continued. Now we're going to look at the Lewis structures for polyatomic ions and some exceptions to the rules. So let's start with a polyatomic ion. Let's look at sulfite. Sulfite is SO3 2-. Sometimes when you have an ion, it's easier to try to figure out how to arrange these by adding up the number of dots that you have or number of valence electrons, keeping in mind what kind of structure it should have to begin with. So if we just quickly look at sulfur versus oxygen, we said our central atom would have the most bonding sites. Well, in this case, both oxygen and sulfur have 2 bonding sites. So which one do we use? Well, in this case, you can kind of tell because you've got 3 oxygens and only 1 sulfur. When you have something like that, your sulfur is going to be your central atom. So I know my structure should look something like an S with 3 oxygens bonded around it. I also know that when it's all said and done, it should have a -2 charge. So I'm going to put my -2 charge on there right now so that I don't forget. All right, from here, again, I like to do a count. So I know sulfur has 6 valence electrons, the 6 dots. Oxygen has 6, but there are 3 oxygens. Okay, and then this -2, we have to remember that means that something gained 2 electrons, so we have to add 2 extra electrons. Okay, that gives us a total of 18, 19, 20, so it's going to be 26 total electrons. Okay, total electrons. Now remember, in an electron dot structure, your electrons are represented by dots. So we need 26 electrons around this structure. Now what you're going to do first is start with 2 for every pair. 1, 2, 1, 2, 1, 2 for every bond. Okay, now every bond has 2 electrons. Then you're going to make sure that your central atom has 8. Okay, central atom must have 8. So when you're doing this, first 2 for every bond. Step 2, central atom has 8. Then you're going to distribute the rest evenly. Making sure you do this in pairs. Keep the pairs together. You're not going to have single electrons. Okay, so I have used up 2, 4, 6, 8. Okay, so I obviously have a few to go. So if that's 8, I go 9, 10, 11, 12, 13, 14. So again, I'm distributing them in pairs. I'm up to 14. I'm going to keep going. 15, 16, 17, 18, 19, 20. Start over, 21, 22, 23, 24, 25, 26. Okay, I've distributed all the electrons. I don't have any more left. And if you look at the individual atoms, this oxygen right here has 8 dots. The sulfur has 8. This oxygen has 8. And this oxygen has 8. So this tells me that my structure is correct. Every single atom has 8 valence electrons. Let's try another structure. Let's look at ozone, also known as O3. You've got 3 oxygens there, so obviously you're just going to have 3 oxygens. Now, if you were to just draw their dot structures with their 6, it's really, really hard to tell how they are going to come together, no matter how you arrange these dots. Any structure where you can't tell how they're going to come together, you can do a counting method. So we have a total of 18 electrons here, because each has 6. 6 times 3 is 18. Again, follow our steps. First, 2 dots for every bond. 1, 2, 3, 4. Second, make sure the central atom has 8. So that's 9, 10, 11, 12, 2, 4, 6, 8. I can't even count. All right, so now I have 8 around my central one. I have 10 more to distribute. Again, distribute the rest evenly in pairs. So I have 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now, if you look at this one, it's not quite right. The one on the right, or on the left, has 8 valence electrons. The central atom has 8. And then your one on the right only has 6. That's not enough. Now, if you remember, if we go back to what we talked about in the first set of notes, when you don't have enough, a lone pair can be shared. That gives you a coordinate covalent bond. So if we look closely at this, our central oxygen has unpaired electrons that it could share. So that's what's going to happen. This is going to move here, and it's going to share it with this electron. So our structure becomes a double bond on one side, with still the 2 lone pairs there. Remember, you still have a lone pair here. You've got a shared pair here, and then you've got 3 lone pairs. Okay. If we look at this as a structural formula, single, double, and then 3 lone pairs, oxygen, and then this 2 lone pairs, and this one still has 1 lone pair. Okay, but they all have 8, because if you take a closer look at this now, 2, 4, 6, 8. You look at this one, 2, 4, 6, 8. You look at this one, 2, 4, 6, 8. They all have 8, so we're good. Now, when you're doing this, it really doesn't matter which side that you put the double bond on. We could always have written it this way. Just keeping in mind your single bond would still have the 3 lone pairs. Now, in nature, these 2 bonds actually look identical. Every bond has a length. A single bond has a certain length, a double bond has a certain length, a triple bond has a certain length. In reality, in ozone, these 2 bonds have a bond length somewhere in between a single and a double. And their explanation is that this extra pair actually gets shared evenly between the 2 bonds. Okay, we call this a resonance structure. Let me spell it correctly. Structure. What does that mean? It just means, oops, you can't read my U. That's a U there. It means that a double bond can be written in more than one spot, or drawn. Can be drawn in more than one location and still meet the rules, the octet rule. Okay, so in other words, resonance structures only occur when you have a double bond, and that double bond could actually be written in a different place but still represent the same compound. Next, we have to look at exceptions to the rules. Exceptions to the octet rule is what it really is. Okay. Remember, the octet rule is telling us that every atom in our structure has to have 8. There are 3 exceptions. 1, the central atom has more than 8. 2, the central atom has less than 8. Or 3, the molecule has an odd number of electrons. All right, let's take a look at a couple different examples. We could look at BF3. Now again, you could count or you could draw, but when I see the term exceptions, I typically look at the structures. I do not count. So if I look at boron, it has 3 dots. And then I look at fluorine. and it has 7, and there's 3 of them. Okay, you can tell which one's going to be your central atom, okay, the single one or the one that has the most, the highest bonding capacity. This has 3, this has 1. You can kind of tell where they're going. You've got a fluorine. One can go there, one can go there, and one can go there because fluorine needs one. So that gives us a structure that looks like this. So you've got a fluorine here. You have a fluorine here. And then you're going to have a fluorine here. This is an exception to the rule. So I'm not going to try to force 8 around the boron. Boron cannot hold a double bond. So this is the correct structure. Why is an exception? Boron has 6, not 8 valence electrons. That makes it an exception. All right, next, let's try another example. Let's look at PCl5. PCl5. Again, I'm going to tell you that it's an exception to the rule. Okay. I look at phosphorus. Phosphorus has 5 valence electrons. 5 valence electrons. Look at this. 5 things are bonded to it. Okay. So I'm going to rewrite this over here because, oops, that should be a single. Okay. Chlorine. You got 5 chlorines coming in. So 1 chlorine can come here with its 7. 1 chlorine can come here. So you got 1, 2, 3, 4, 5, 6, 7, 8. Another chlorine can come here. 1, 2, 3, 4, 5, 6. So it will have a total of 8. Now you've got your 2 electrons that are up here. I've only used 3 chlorines. I have 2 chlorines left. Where are they going to go? They're going to squeeze in here. One's going to go right there with its single electron. And one's going to go in here with its single electron. Okay? So phosphorus, in this case, has 2, 4, 6, 8, 10. 10, not 8 valence electrons. So it's an exception because it has more than 8. More than 8. Those are usually pretty easy to see. For example, I could say sulfur hexafluoride. Well, sulfur has 1, 2, 3, 4, 5, 6. And there's 6 chlorines. What does that mean? You're going to have 1 bonded there, 1 bonded there, 1 bonded there, 1 there, 1 there, 1 there. 2, 4, 6, 8, 10, 12. 12, not 8 valence electrons, because each fluorine is going to bond on one of the 6 valence electrons that are there. So again, it's an exception to the rule. Another one that we see, NO3. Okay, NO3. Here you've got N, you've got 5 valence electrons, you got oxygen, with each oxygen having 6. You can't tell where they're going to bond. Okay, so in this case, I would do a count. Okay, so nitrogen has 5 valence electrons, oxygen has 6, and remember there's 3, so you have to add those together. So we're going to have 18 plus your 5, which gives us 23 electrons. Without even drawing it, I know that it's an exception because it has an odd number. Okay. The actual structure is quite strange. You get a double bonded oxygen and a single bonded oxygen. And then you have leftovers. So 2, 4, 6, 8, 10, 12, 14, 16, 18. I think it's like that. All right. So anyway, you don't even have to draw the structure because we know it's an odd number. All right. So you have some samples like this. If it doesn't say it's an exception, you make sure it has 8 valence electrons. If it has an exception, you're looking for an odd number, more than 8 or less than 8.